Greetings, everyone. Happy Friday from wherever you are. We're excited to have you with us. I guess I should say good morning, good afternoon, good evening. Some of you are late into the evening, but we appreciate you joining us. Let's just give folks another minute or so to join us, and we'll get started. At the end of the webinar today, I'm going to provide you some additional information on the upcoming IWCS conference in October. It will be in Pittsburgh here in the USA, but hopefully you're considering call for papers. So, I'm submitting an abstract for the conference this October. So I'll provide a little information on that at the end, but you'll also be receiving it in your inbox as well. So let's wait another minute or so. Well, let's go ahead and get started. There'll be a few people fashionably late, but again, thank you for being with us today. My name is Dave Cadu, and I'm honored to be the CEO and Director of IWCS, and I'll be your moderator for today. We do have a very wide audience from all over the world, and we're very thankful for you to be with us. And for those of you who weren't with us last month, Happy New Year. It's going to be a very exciting year, and today's presentation is going to be really a nice setting for a lot that's happening in our industry this year. A few housekeeping items. As an attendee, you're part of the larger audience. So during the presentation, all participants will be in listen-only mode. And also, this event is being recorded for rebroadcast. It will be available on our website shortly, within a week or so you can share it with your colleagues or watch it again if you wish. We encourage you to submit written questions at any time during the presentation using the chat panel on the right of your screen. So use the chat to type in your questions at space in the space at the bottom, and then make sure you hit the send button, and your questions will be addressed, time permitting, at the end of the presentation. So again, this webinar event is being hosted by the Cable and Connectivity Industry Forum. And today we are really honored to have Mabood Chowdhury, the Standards Manager for OFS in Massachusetts, USA. Mabood will be presenting his paper on fiber optic links for artificial intelligence computing and networks. Again, a very topical subject. Mabood is the Standards Manager for OFS. He contributes to IEEE 802.3 Ethernet, the INCITS T11 fiber channel, and the IEC fiber standards. He is the Vice Chair for IEEE P802.3 DH, the 100 gigabits per second, 200 gigabits per second, and 400 gigabits per second short reach fiber task force. Mabood has a master's degree in mechanical engineering from Massachusetts Institute of Technology and a bachelor's degree in mechanical engineering from Duke University, two really fine institutions. So Mabood also holds 32 US patents. So welcome, Mabood, and thank you for presenting at today's IWCS webinar series event.
So Dave, thank you for that introduction. Started to share my slides, so hopefully everybody can see that.
Looks good, yes.
Okay, thank you. So Dave, thanks for that introduction, and thanks for everything that you do from IWCS. You know, the topic here is fiber optics link for artificial intelligence and computing and networks. So artificial intelligence clearly is a topic that I think everybody is well aware of today. It's one of the key technologies in the world today. But connectivity, whether it's the cabling and connectors and the physical layer, is always key and important. So I think that'll be our topic. And again, as Dave said, appreciate everybody joining from around the world. So I'll also say my good morning, good afternoon, good evening. I know for some of you it's about to be Saturday, and if you're on the West Coast, it's early in the morning, West Coast US. So the agenda for today, quick introduction, then we'll talk about AI data center market drivers. Standards update. As Dave indicated, I spend a lot of my time in standards, and I'll do a quick update. I was the vice chair for the 802.3tb project. That project finished. It's a published standard at this point, but still very active in IEEE 802.3 Ethernet, where almost all the physical layer specifications are written in the Ethernet space. So even if it's InfiniBand or UIC or other standards, the physical layer standards typically come from IEEE 802.3. Fiber channel, IEC, and actually a lot of stuff going on ITU-T in that regard. So I'll touch on that. And then as we get this sort of need and market driver from AI data centers and networks and clusters, what are some of the fiber optic technology options that are available that either are deployed or becoming standardized, being driven by this tremendous demand that's coming in data rates and bandwidth from AI networks. So again, first area is AI data center drivers. And I'll take a step back for a second, sort of where we are today. A lot of things, I think, in terms of artificial intelligence and generative AI and large language models, I think came into everybody's view with ChatGPT announcement in November 2022. As with any technology, the history is much richer and deeper. It goes back decades of people working on this area for a long time. This presentation is from IWCS 2024, which we had in beautiful Providence, Rhode Island last October. October is when Geoffrey Hinton and John Huffield won the Nobel Prize for their work in this area for neural networks, for what's become now large language models and generative AI. So, this work is now very much focused around the world. There was an AI summit in Paris just last week, so it definitely draws the world's attention. A lot of neural networks, I'll say this somewhat carefully because, like with any analogy, they aren't perfect, but sort of the human brain, the way it operates with 100 billion or so neurons and trillions, 100 trillion connections, and does it actually remarkably efficiently from a power perspective. It's about approximately 20 watts to do what the human brain does. And there's a quick comparison there of the number of stars in the Milky Way. It's about 2 to 400 billion. So it's a huge amount of processing that goes on. The brain's actually remarkably efficient in sort of being in sleep mode. It shuts down most everything, and that's why it's very energy efficient. And as it does this computing, so to speak, and it achieves a state of intelligence, sentience, and obviously the capacities that we know. If you've ever observed a little baby or a kid and how they learn and develop. So a lot of that has been the foundation of the inspiration for what's happened in this area with neural networks. Dave mentioned that the next session in 2025 IWCS will be in Pittsburgh, and actually that's the home of Carnegie Mellon University, among many other universities. Hinton actually was at Carnegie Mellon when he did some of the foundational work with backpropagation, and also with a lot of the work that he did subsequently at the University of Toronto and then Google. And so hopefully we'll get some of that connection to CMU and IWCS. It would certainly be in wonderful Pittsburgh. Hopefully everybody will join that important conference. Hinton's also been sort of famous in terms of warning about the safety of AI. So there's always this huge promise of this sort of utopian vision. There's also, for those of us who watch or read science fiction, there's a dystopian vision. So there's a lot of work going on in that regard. So in terms of the world that we deal with, and it's not just one company, but NVIDIA has been very prominent here with their GPUs. Google has done a lot of work with its tensor processors. There's other companies, obviously AMD. There's a lot of Chinese and European companies that are very active in this area. But essentially, these GPUs are acting analogous to the neurons. Those are the nodes. And you're creating these vast networks, and you need connectivity. In the brain, that's an electrochemical, biological connection. For data centers, that's copper and fiber. So you still need that, and you still need an awful lot of connectivity to make these networks reality, and the demand that's required for that, and the power that's required for that. So being energy efficient, having high density, having really the highest bandwidth and data rates, that push is tremendous right now. So this is just one view, and I'll start by saying it's US centric, but as we know, the work that's happening with AI is very much global. When I made this presentation, I hadn't. I don't think most of the world had heard about DeepSeek, which made some announcements a little while ago that very much shook the entire AI industry in terms of how efficiently you can make these models happen. They set quite a benchmark there. Besides the source that I have here, which is really capturing the sort of a chip count in terms of the almost arms race of how large these AI clusters can become. The largest one shown there is from xAI. This is Elon Musk's AI company, and it's Grok 3. It's the Colossus data center that was put up in Tennessee, United States. So that's the largest AI cluster using 100,000 H100, H200 NVIDIA chips, which are some of the hottest GPU chips on the market today. And the question is, how large is this going to go? Do you go to 200,000? Do you go to 1 million of these? As I said, DeepSeek and a lot of other open source large language models are sort of challenging how efficiently that can be run while being highly effective. But that's really a lot of where the drivers are. There's another site which I'll mention, which I think people might be familiar with, which is Hugging Face, which is a Franco-American source that looks at open source large language models. And there's a whole variety of institutions, countries, companies that are very much driving this technology forward. The next slide I have is a slide taken from Light Counting with their permission that shows basically how the growth in terms of optical transceivers. Light Counting does an excellent job in terms of looking at both historical data and then making projections of where they see things going. And the biggest component, so the cloud portion, that cloud hyperscale data centers and enterprise data centers, those continue to be there. That's shown in red. But the largest growth is happening with AI data centers in terms of going forward, and there's obviously other applications too. So again, in terms of, this is a little bit NVIDIA focused, there's lots of other topologies. So this is just one of many. Obviously, NVIDIA plays a large role in this market. It's basically, I'll mention a quick personal thing. One of my adult children back in 21, right during the sort of peak of COVID, was building a gaming PC, and they couldn't get hold of the NVIDIA chips that they were used to ordering. So NVIDIA, just a few years ago, was probably known for those parallel processing for gaming type PCs, and that application has become enormously successful in the AI space thanks to that parallel processing capability. And it's not just the chips, it's the entire computer stack where they've really taken. But again, being challenged as in a competitive world by lots of other companies too. So it's basically, it has both copper, it has multi-mode from SR4 perspective, and it has single mode from a DR4 perspective. MPO12 connectors, so 12 active fibers, excuse me, and the number of GPUs keeps growing. And latency is important in terms of what's there, as is basically density, all becomes key factors in moving these technologies forward. So in terms of the sort of from a multi-mode perspective, it's been SR8 That's been very, very successful. It's dominated. So 800G SR8, which was, when I get to the standards, it was a DF standard that was introduced at the beginning of 2024, has been dominant there. It's 70% of the links are in that space. For longer reaches, you have single mode DR8, that's there, as well as single mode FR8. So all of these copper and fiber applications have been in high demand as we've looked at these AI clusters that continue to keep growing. And this is just from NVIDIA spends a lot of time in InfiniBand. InfiniBand has a long history in terms of high performance computing and that market. But again, if you dig into it and you look at the physical layer specifications, they tend to point back to IEEE and the 802.3 Ethernet standards. And in terms of transceiver speeds, links by speed, what you're seeing is things going rapidly from 400 to 800 with projections at 1.6 terabyte coming forward. And there's already discussions about 3.2 terabyte type speeds in the horizon. In terms of multi-mode solutions, this really has been for a very long time the most efficient and reliable short reach links. So in the enterprise space and in the cloud data center space and in previous generations, that's typically been 100-meter type reach on OM4 type /OM5 type fiber. OM3 supporting a shorter reach than that 100 meters, usually around 70 meters. For these AI clusters, most of those reaches have been 50 meters or less. So up to 30 meters or up to 50 meters covers most of the application needs from an AI network or clustering perspective. And again, what you see here is if you look at what I mentioned about the 800 gig SR8, that really has been the dominant transceiver and optical speed going, but that's been deployed to date and will continue to be deployed in the next couple of years. So switching to sort of a standards perspective, and as David indicated in my bio, I spend a lot of time in standards. I always have to be careful. Standard is one view into this world. There's lots of other views. So standards has historically played a valuable role there in creating industry solutions that are interoperable. But there's MSAs, there's proprietary solutions, there's lots of other technologies and topologies. There's open source work, there's closed proprietary networks. But again, from a standards view, what I'll start with is now a slightly older slide. So these have been updated since the presentation last year. But the two standards that came out here, that DF standard was the one that published at the beginning of 2024. So the way IEEE works, 802.3 works, before you publish the standard, there's 3 generations of standards, draft standards that happen. 1.x, which is an initial version, as people within that group debate it and discuss it and develop it. 2.x, where things are becoming more technically stable, and often you'll start seeing commercial solutions based on that technically stable solution. And then the 3.x standards, which basically are the final review and updates before it gets published. So that DF standard has been deployed. That was built on 100 gig per lane. The existing standards there on the single mode side was the .3U standard, 802.3CU, and then 802.3 dB in terms of the standard on the multimode side, and 802.3 CK on the electrical side. So these 3 components allowed that standard to go forward with DF, which enabled those speeds to go up to 800 gig and 1.6 terabyte by essentially having multiple lanes, but still operating at 100 gig per lane type speeds. And actually that was capped to 800 gig. The 1.6 happens with the 200 gig per lane. So that standard is the 802.3 DJ standard. And just from a nomenclature perspective in IEEE, that capital P in front of the standard means it's an active project, while the published standards, that capital P is dropped. So that's what that means. So that's probably the single largest project right now in 802.3, certainly in the data center type space. It's the largest project with lots and lots of participants. Just a quick note on IEEE. That operates, it's an interesting standard in that you participate as an individual expert or participant, and you indicate your company affiliation and employment. That's different than most standards where you're usually participating as a company, as is the case in Fiber Channel or TIA, or by country, as is the case in IEC, ISO, ITU-T. So that's an interesting historical fact in the way 802.3 operates. So in DJ, if you look at it, and the red is the DF, the published standards, and if you look at the other colors there is no multi-mode standard, but there's multiple copper and single mode standards that are being developed in the DJ project. And again, somewhat dated, this shows to when you go from basically proposed baselines to adopted baselines. So this project is at this point in what's called task force review. So that's the 1.x standards. It's rapidly progressing. I won't predict the future. You have to be careful in that regard in the standards because the group has to, meet its timelines. But it's projected by the middle of this year to go to the technically stable standard. That means there will be no more TBDs or to be determined values. There'll still be lots of meetings and contributions. The way these standards move forward is lots of technical contributions from these experts affiliated with different companies that moves this project forward. The chair for that group is John D'Ambrosa, the vice chair is Mark Noel, and really an excellent leadership team there, the editors, et cetera, that are driving that project forward. I just wanted to touch on some of the work that happened between IEEE and ITU-T. So there was a lot of question about, this is on the single mode side, on the G.652 standard for zero dispersion wavelength fibers, sort of the standard generic single mode fiber, if you will, that's deployed across the world. In terms of looking at the chromatic dispersion, the polarization mode, and the group differential delay, those parameters. So the agreement was not to change anything on the normative standards. So G.652 is still the same fiber, but there was a lot of work to look at statistically what are some ways to adopt that those numbers, those parameters, and still allow direct detect technology, so IMDD type technology, to continue to be utilized for the single mode optical PMDs. So that work was achieved to support essentially things that go up to 2 kilometer and 10 kilometer type reaches. If you go beyond that, the specifications turn to coherent, which takes into account both amplitude and phase. So they can be more tolerant in terms of what those fiber characteristics are. But coherent tends to be historically more complex, not as cost effective than the direct detect technologies for those intermediate type reaches. On the multimode front, the work really is saying, so as I mentioned in DJ right now, there is no 200 gig per lane multimode standard, but that demand continues to be there. So there's always this question from a technical feasibility perspective, if VCSEL's multimode links can move up to that. Having participated in the previous 2 generations, the same questions arose with 50 gigs per lane, that became the 802.3 CM standard, and then with 100 gig lanes, which became the 802.3 dB standard. So those same questions have remained there. Is our VCSEL multimode links going to remain relevant? From a demand perspective, as I mentioned, probably 70% of what's deployed today in the AI clusters for those short reaches. This is, for copper, you're good to about 1 meter or so. If you go up to 30 or 50 meters, it still tends to be multimode quite dominantly. And if you go beyond that, it goes to single mode. And so if you look at the projections, light counting, 650 group, others, there's a need for 1.6 terabyte SR8. So basically 200 gig lanes is sort of the market driver or need. And the question is, what's technically feasible? So in OFC last year, there were multiple companies that showed technical feasibility up to 30 meters This is a Broadcom eye diagram that's shown here. People are attending OFC in a month. There'll be more announcements, more demonstrations. Again, multiple companies. I mentioned Broadcom, but Coherent, Lumentum, Huawei, HiSilicon. There's several companies that have continued to show technical feasibility there. The other work that's happened is on the BiDi front. So there's a terabit BiDi MSA that was published a while ago. So basically, you're looking at two wavelengths instead of one, 850 and 910 centered wavelengths with a range around that. And there's a complementary, quote unquote, OM4 plus standard that OFS produces, that Corning and others also produce, that basically optimizes the fiber for those 850 and 910, where an OM5 would extend that all the way to support SWDM4 for 940. 953 is what the standard actually allows for. So that's published. I will say that BiDi has been historically 40 gig, 100 gig, very successful in the enterprise space. It has tended not to be used as much in the cloud computing space or in the AI cluster space, partially for power reasons, but also in terms of the number of suppliers. So even though an MSA includes multiple suppliers, as the name is written around, multiple supplier agreement. But IEEE 802.3 tends to provide more of an interoperability across multiple vendors as long as you meet those specifications. So this slide just goes into a little bit about there are longer wavelength options for multimode. And so especially in fiber channel, which tries to maintain a 100-meter reach, that BiDi solution may be what's more appropriate. Fiber channel also tends to be more of an enterprise solution. But in the Ethernet space, that 850 wavelength, single wavelength, still tends to be the dominant thing. And again, we'll see if and when that project starts in 802.3, what that wavelength or wavelengths might be. But if you look at it from a fiber perspective, the longer wavelengths give you lower chromatic dispersion, lower attenuation, and you can achieve longer reach there. So there was a specification 802.3CZ in IEEE for automotive applications. So automotive has historically not been fiber. It's been copper, twisted pair, or coax type cabling. And that specification was written around a 980 pixel specification. It's still OM3 type fiber that's rated at a much, much higher temperature to support automotive applications. But again, because those reaches are limited to 40 meters, typically a 980 pixel and OM3 type fiber specifications was adequate. So the question is, what's going to be available what's going to be required to support 30 meters or 50 meters at 200 gigs per lane has still to be determined. But OM4 tends to be the sort of dominant fiber in that space. So in terms of fiber development and some high density cables, I'll go through some of that. So the first technology is rollable ribbons. Again, the issue is, well, how do I get higher density and still maintain usability? So rollable ribbons are partially bonded ribbons that are rolled into a cylinder. So it has some of the advantages of being ribbonized, but it also has the packing density because you can roll it into a ribbon type fiber. And so there's been multiple solutions from multiple companies in this area. So OFS Furukawa, which is our parent company, has some solutions in this space, as do others, that again allow for a much higher density solution. Something that's, again, a recent development is with improved fiber coating technology. There's also a multi-mode solution, rollable ribbon that we'll be introducing at OFC and is available at this point. Chart or slide shows the advantages. If you start with a sort of 72 fiber tight buffer solution at 19.2 millimeters, if you go to a flat ribbon, that goes down to 12.7 millimeters, and the same 72 fibers in the rollable ribbon become 6.2 millimeters. So you can see, a 34% reduction, then an additional 51% as you go from a loose tube type design all the way to a rollable ribbon. And the chart on the right side of that slide, what you're seeing is that, again, that advantage, this is now with a 288 fiber ribbon going to a rollover ribbon. And then instead of a 250 micron fiber, using a 200 micron fiber. So that reduced diameter fiber, which is deployed now in many parts of the world and is reliable, gives you a further reduction of that density. So the other issue is that we're getting into this capacity crunch. Historically, every 10 years or so, there's a 10x increase every 4 years or so. That's happened, starting from the early 80s all the way to the mid 2000s. But that need for capacity is increasing dramatically. And the biggest one, which is that top right-hand corner, is basically with AI clusters that are going 9x every year. So the demand and the need is enormous for us. So a single core solution just becomes a challenge to meet that requirement, no matter how tightly you pack them. So there's been quite a bit of work already in the multi-core space. So you're putting multiple cores instead of using a single core. Lots of designs have been implemented there. In terms of applications, ocean or undersea fiber, where again, obviously, getting more fibers in a tighter space is important, has been available, but it's also now entering into the data center space. And so you can do this with either single mode or multi-mode. Both are possible. Basically, the advantage is that if you look, again, from a packing density perspective, this is looking at it, and this is going to be US measurements, 12 inches by 8 inches cross-section in a data tray. Again, you can start with that 288 fiber flat ribbon, go to a rollable ribbon, go to 200 micron. And so you go from basically 110,000 fibers to 140,000 almost fibers to, if you do 4 cores, you're almost at 560,000 fibers. And if you go to 8 cores, you're all the way at 2.2 million fibers. So that's sort of, the figure illustrates the advantage of using multiple cores. So a colleague of mine at OFS, Yi Sun, and actually in partnership with some folks at MACOM, we looked at combining 53 gig linear PAM4, so a multi-mode, four core multi-mode fiber, and using linear optics to show a low power solution, essentially. So a combination of both multi-core, multi-mode, as well as linear optics. Before I move on, I'll quickly mention from a standardization perspective. So I'll go back to this sort of multi-core in general. There's active work now, active projects in both ITUT Study Group 15, Question 5, and in IEC 86, SC86A, Working Group 3, in terms of this liaison work between these two organizations, looking at 2-core and 4-core weakly coupled fibers. So making those standardized and therefore interoperable. ITUT certainly from a sort of more overview systems level and specifications, and then more on the detailed measurement specifications. And again, a lot of crosswork between the two standards bodies in IEC and ITUT. Those projects became active late last year. IEC in its October meeting approved that as a new project, and ITUT in December met and started having these discussions. So that work is definitely happening. All of that work right now is single-moded. There is no multi-mode variant there. So it's 2 and 4 core single-moded. In terms of the other fiber type that I want to mention that addresses the need being driven by AI clusters is, excuse me, a hollow core fiber, which is sort of the ultimate latency reduction fiber. So what you see here basically is that light travels faster in air than in a solid core, a glass fiber. So the same, let me see if my animation will work here. Right. All right, it may not, but basically the idea is that because the speed of light in a glass core is 204, 190,000 kilometers per second, and the speed of light in the hollow core is 301 kilometers per second. You can get much faster transmission through there. And what that enables you to do is for any sort of fixed latency, if you've got a particular number, the reach distance increases by 46%. And so you can deploy fiber in a longer reach and still have the same latency. And for a fixed distance, latency is reduced by 1.55 microseconds per kilometer, or by 31%. So the sort of very short reach, what's already been deployed is things like high performance computing and financial networks, where even a very small difference in latency translates to huge financial benefits. It's already deployed there. In longer metro network, it's also being deployed. And that top part, which alludes to the fact that you can basically go further out, has real implications in terms of power supply and power. The need for power. I think people have probably seen the recent announcements of multiple companies looking at nuclear power as a source for their AI data centers. So that requirement power is huge. The ability of having the flexibility of the fiber to go further benefits those AI data applications additionally. This is a chart that was, or a slide from ECOC in Europe last year that shows a technical feasibility and actual deployment that happened, 9.22 gigabaud, 16 QAM transmission, and basically on about a 1.4 kilometer. And what you're seeing again is that same reduction in latency that's there. So that's the advantage of hollow core that is being deployed. There's an OFS product here, but there's multiple companies with a couple of key technologies in terms of what's being deployed and created in hollow core fiber. So I'll go into my conclusion slides here. And essentially, because of the need driven in the past by a lot of the hyperscale cloud, that continues to be there. But in addition to what AI clusters are requiring at an accelerated rate, and I'll tell you as somebody who works in standards, it's stressing standards and the entire ecosystem. We're asking for higher and higher data rates, faster data rates at a much higher speed than historically has been there. I didn't mention this when I covered the IEEE slides. In January, there was a meeting in Phoenix, Arizona. First, basically presentations around looking at beyond 200 gig, so most likely being 400 gig per lane, so per wavelength type applications. It's already being discussed. I mentioned the person who's the chair for 802.3 DJ. He's also leading the effort, John D'Ambrosio, for this effort to look at greater than 200 gig for AI applications. It'll draw in lots of experts across the industry, lots of end users, lots of people within the source. So that's already beginning to happen, and that will end up supporting 3.2 terabytes in terms of multiple lanes. So as that demand comes in, looking for compact fibers and high density cables becomes important, and rollable ribbon reduces the size and ease of routing. So that's definitely there. It's ideal for multi-fiber connectors and mass fusion splicing. And there's now also the single mode rollable ribbon cables, and now there's multi-mode rollable ribbon cables in addition to it. From a fiber perspective, so that there's still, for very short reaches, a copper need and electrical specifications that are there. From a fiber perspective, it's multi-mode and single mode that goes forward. So multi-mode pixel solutions have continued to be the most widely deployed short reach solution, less than 100 meters, and now that's more less than 50 meters or less than 30 meters. 200 gig VCSELs are in development, and this 2025 calendar year, I think you'll see activity both in terms of technical feasibility and also standards development work that'll happen there. But that's yet to be announced or implemented. In terms of what's already happened, the 800 gig SR fade SR8 tends to be the dominant. Roughly 70% of AI links are in that space. And the future is basically, and again, it may not be directly in the AI space, but in other areas, looking at longer wavelengths, looking at more wavelengths, looking at multiple cores. As I said, in the shorter space with 200 gigs, it's likely to remain more in the OM4 850 nanometer space in terms of wavelength. In terms of single mode solution, even single mode, which is designed obviously for much longer reaches, there's questions about looking at a statistical view of chromatic dispersion, PMDQ, and DGD, differential group delay. And so 200 gig lane draft specifications are already here in 2025, and that project, which is Ethernet3DJ, will complete in 2026. In addition, to deal with, again, this sort of high density, low latency fiber solutions, multi-core fibers are another both concept, but now reality in terms of what's deployed. And we expect future, density increases and deployments. There's active work in both ITU-T and IEC to standardize those types of fibers. Again, 2 and 4 core weakly coupled for now, and to make those industry standards and interoperable. There's both fan in and fan out and direct attach type transmitter type options that are available. So it can be a solution and co-package type optics in addition. In terms of sort of the ultimate low latency solution, hollow core fibers draw increasing interest, and there's a lot of development there. As with any new technology, even though hollow core has been around for a while, when you deploy it in very large volumes, solving the sort of production issues, being able to scale up is important, is sort of key. In the AI data centers, what really matters is the sort of back end scale up and scale out portion. But in any technology, the ability to scale up becomes important. And so that's really what hollow core fibers is dealing with right now and addressing for solutions. So just again, a sort of summary of just the conclusions I went through. Higher data rates, there's 400 and 800 gig already being worked on, and we're going to go beyond that with 1.6 and 3.2 terabytes. 100 gig lane and 200 gig lanes are currently being worked on. Certainly, 100 gig lane is developed and deployed and very successful, multi-mode and single mode. 200 gig lane is being worked on in the single mode side, and the expectation is there will be work on the multi-mode side, hopefully in 2025. And again, there's sort of higher density and better usability solutions with rollable ribbon and multi-core fiber, and lower latency is hollow core fiber. So both, a real need for both multi-mode and single mode. I'll finish by saying, whether it's AI clusters, hypercomputing. Right before this, Dave is at a conference supporting quantum computing. You still have to have a physical layer. You still have to have cabling. You have to have connectivity. And as those application drivers push the technologies, a lot of ideas, sometimes that have been around for years or even decades, get the resources, get the creativity, get the companies to actually make commercial success. And again, IWCS has always played a great role in bringing us all together in addressing those things. So thank you again for your time. And I know there are questions coming in. So Dave, I'll let you address those.
Mahmood, extremely enlightening. And of course, it's visionary. There's a lot of work to be done in terms of performance. And then, of course, the nuts and bolts and the hardware and the networks that have to make it happen, and some of those technologies that are being developed was very, very informative. So, thank you tremendously on behalf of all of us. One question that kind of came up is, you talked about AI clusters. Is the requirements, what's the limiting factor right now in terms of requirements for the infrastructure that we're talking about, whether it be fiber or the copper layer? Is it the data center internal cable networks, or is the outside plant and the long distance network is where do we need the most immediate work done?
So certainly what I presented looked at that sort of within the data center piece of it. And within that, we've tended to focus on that server to switch and lower level switches to higher level switches connection. So we've had that for a while, again, within the data center. What AI has introduced is this back end piece of it. And that's really where the huge explosion of growth has happened in the connectivity. And that's where its copper is a 1 meter, multi-mode's been 30 to 50 meters. And if you go longer than that, it tends to be single mode. But your question's an important one because in order to support those data centers, you need the intra data center work, you need the whole deployment, you need smart grids, you need to do the power management. So in one sense, the answer is all of those. I did focus very much within that. And again, this piece that frankly, we weren't addressing even a few years ago. It's sort of come up very rapidly. It used to be in the domain of high performance computing. So companies like IBM and others and InfiniBand have looked at this for supercomputers for a long time. But I don't think anybody envisioned 100,000 GPU, Grok data center just a few years ago. Like I said, it's sort of almost like in a blink, you've gone to these. So that's putting tremendous pressure. But as with pressure, necessity is the mother of invention. You come up with creative solutions. But your question, or whoever asked that question, it requires a complete solution of the entire overall network to be able to support this. You've got to be able to power this stuff. So as I said, evolution, God, wherever your belief system is, the brain's pretty efficient in doing this. We got there. Most of these networks are not. There's been a lot of brute force computing that's gone on, but it's one data point, and I have a younger brother who's an academic who spends his life in this space. There's a lot of people looking at how to do this stuff efficiently. It has to be done more efficiently. You can't simply take the existing models and keep extrapolating, just double the data rate, double the power. Like we literally will run out of power on the planet if we do that. So I think we have to look at all of that.
You mentioned the smart grids and the importance of these clusters or circles. Do you see AI, one of these AI clusters being at the edge? You can talk about mega data centers and hyperscale and all that, but really breaking it down into the edge data centers. Do you see that happening?
Because again, you have to deploy this stuff. You have to look at latency of all of these things. So I'm hesitating a little bit because I have enough gray hair to have lived through the dot-com bubble and the telecom bubble. So there is this sort of how far does this hype go and does it pull back at some point and what's there? But the promise and the projections are it'll touch everything. There isn't any part of the network that it will not touch, including, I'll give you a personal story. I got in a Waymo taxi in Phoenix a few weeks ago, driverless, which is autonomous. And for those vehicles, it took a little, I had a lot of hesitation getting in initially, but after about 5 minutes, I was like, this works, this is good. I mean, it took me from my hotel to my airport and I got there. So I can't think of an area that this won't touch, not just the edge, but every part of it, how it does it, how we deploy it. And, Dave, I keep mentioning this. I think IWCS, as with IEEE, as with a lot of these standards bodies and industry associations, helps implement these things in a practical, real way, as opposed to the visionary things. The visionary things are there. And like I said, I grew up on science fiction books, like I guess most engineers or something. So lots of possibilities in lots of directions. But we have to do a good job of that.
Yeah, one last question, and it's referring to your slide 22.
Yep.
Could you kindly elaborate on how splicing was resolved?
How splicing was resolved. Okay. So I don't know that it has been resolved. Each company has solutions that support it. So this is not, you don't do this in the field. It's not like other technologies that way. So in a controlled way, it can be done. As I mentioned, I'm certainly not the expert within our organization in this. For ocean cable and undersea cable, this has been deployed and handled. And I think how you handle that question is an important and a good one. How you do that, and that's really where an organization like IEC and ITUT add a lot of value. How do you do this in a way where it can be interoperable in the way we deal with single core today? Single core has lots of options in terms of how you splice things together. Anything can be engineered, anything can be sort of custom designed and kept proprietary. But when you expand that to things that are interoperable and standardized, there are some real challenges there. But these are not just lab type products. These are products that have been deployed in the field, and all these issues have been addressed. But to make it available for data center generic, sort of general purpose use, there will be a lot of standards battles and disagreements. And the way standards works is eventually you build a technical consensus and you move forward in a way that's best for the industry and customers.
Precisely. So again, we've covered an awful lot of ground, and we can't thank Maboot enough for just what's on the horizon. And it's going to be a very exciting next 10, 15, 20 years to see this implementation roll out. But it's going to take all of us. It's going to take innovation. It's going to take understanding what the requirements and the standards are going to be. But again, Maboot, thank you. And for those of you who want to reach out directly to Maboot, if you have specific questions, I've provided here the email address, and you can reach out to him. Again, this presentation will be being recorded and will be available on our IWCS platforms fairly shortly. So I just want to mention that we have these technical webinars each month, typically on the third Friday of every month. So our next technical presentation will be on Friday, March 21st at 10:30 a.m. Eastern USA time, and each of you will be receiving announcements for these events. And of course, please feel free to share these with your colleagues to hear about a lot of these great new innovations and technologies that are coming our way.
Dave, if I could chime in, we're not seeing your PowerPoint screen. If you could share that.
Oh, okay. It's actually showing that I'm sharing. I will stop share and share again. Let me try that. I apologize. Let me share it again. It showed like it was on my screen. How about that? Is
Not
it
yet, but
sharing?
perhaps there's just a lag.
Okay. Can you see it?
No. Maboot, do you see Dave's screen?
I don't. It seemed to go to blank, so it did try to do something, but I don't see content.
Dave,
That's,
carry on, and I'll share the screen from my computer.
Yeah, if you could, that'd be great. And can you step through the slides as we wrap up here?
Yes, no problem.
Okay. Yeah, I apologize. I'm not sure my computer is showing that it's sharing, but if you could call up Maboot's contact points just so everyone has that.
I saw somebody say if we use hollow core fiber, we might get better latency. So I support that comment fully.
Yeah.
I do see that, Becky.
Yeah, I'm seeing a blank screen, but if Maboot can see it, let's carry on.
Okay, go on, Dave.
Okay, so again, you've got Maboot's contact points here. And again, we have our next technology webinar on Friday, March 21st. And again, it's important for everyone to know that our upcoming IWCS conference is going to be in October in Pittsburgh, Pennsylvania. We have a call for papers that is happening right now. We have a deadline in early April, so it's only 6 weeks away coming. It's amazing how fast time is passing, but please consider entering an abstract for your own work or for your company so that that you can share all of the great things that are going on in your world and your innovations with the entire IWCS community. So please, it's easy to find our call for papers on our website and to easily submit an abstract. And also, I want to make sure that we recognize our partner level sponsors who greatly contribute to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and, of course, their generosity, we would not be able to bring these important innovations and information to you and to our global audience. So again, thank you to our leading suppliers in our industry for their strong support of IWCS. Again, for over 73 years, IWCS has presented the Cable and Connectivity Industry Forum, and we are the recognized leader in showcasing these new technologies for products and processing and applications. Our 74th annual conference will take place Monday through Thursday, October 27th through 30th, in Pittsburgh, Pennsylvania at the David Lawrence Convention Center. So please watch your social media, our website, to learn more as the exciting information comes available. And again, please submit an abstract and be a part of the conference program itself. So with that, I want to thank you all for being with us and have a great weekend. Thank you again, Mabood.
Thank you.